Hello, I am Dr. Sachi Vale, and welcome to Science Aura. When we gaze up at the night sky, the moon appears as a familiar, quiet neighbor. Half a century ago, the monumental Apollo program transformed this celestial body into humanity's very first stepping stone into the cosmos. Today, we stand on the precipice of a completely new era in space exploration. The ambitious Artemis program is not just about returning for a brief, historic visit. It is about establishing a permanent, sustainable presence in deep space. To achieve this monumental goal, we must shift our focus from the safe, sunlit plains to a much more dangerous destination. We must conquer the treacherous and mysterious lunar South Pole. This shift represents a fundamental evolution in our approach to spaceflight. We are moving away from the short, highly choreographed camping trips of the past. The new objective requires robust infrastructure, advanced technology, and a mindset geared towards long-term survival. The South Pole of the Moon offers the perfect, yet perilous, testing ground. Why trade the relative safety of the lunar equator for a region fraught with extreme hazards? The answer lies in the fundamental requirements for sustaining human life off-world. We need resources that are too heavy and far too expensive to constantly transport from Earth. The South Pole harbors secrets that could unlock the entire solar system. In Greek mythology, Artemis is the twin sister of Apollo. It is a fitting name for a program that builds upon the foundational achievements of the 1960s while charting a bold new course. Where Apollo proved that humans could reach another world, Artemis aims to prove that we can adapt, survive, and eventually thrive in the harsh environment of deep space. However, the environment waiting for the next generation of explorers is vastly different from anything encountered before. The lunar South Pole is a landscape defined by brutal extremes. It is a place where blinding light meets eternal darkness, and where the terrain itself seems actively hostile to mechanical and electronic systems from Earth. To understand the sheer scale of the challenges ahead, we must first look back at the historical context of lunar exploration. The technological leaps made during the mid-20th century were nothing short of miraculous. Yet, by modern standards, the computers and materials used half a century ago were incredibly rudimentary and highly limited. Today, we possess computational power and material sciences that the early pioneers could only dream of. We have advanced robotics, artificial intelligence, and autonomous navigation systems. But even with all these modern advantages, the physical realities of the lunar South Pole present engineering hurdles that push the boundaries of current physics. This documentary will delve into the monumental technical challenges of the Artemis program. We will explore the razor-sharp dust, the bone-chilling cold, the treacherous topography, and the psychological isolation of operating far from home. We will examine how scientists and engineers are working tirelessly to overcome these unprecedented obstacles. But before we confront the daunting future at the lunar South Pole, we must examine the legacy of the past. By understanding how the early missions operated in the relatively benign conditions of the lunar equator, we can fully appreciate the immense leap in complexity required for the new era. Let us journey back to the sunlit plains of the Apollo era. The early lunar landing sites were carefully selected with safety as the absolute highest priority. Mission planners targeted the vast, flat basaltic plains known as Maria, located near the lunar equator. These regions offered a clear, unobstructed approach path and a relatively smooth surface, minimizing the risk of a catastrophic landing failure. Operating near the equator provided another critical advantage: predictable and abundant sunlight. The missions were meticulously timed to land during the early lunar morning. This ensured that the sun was low enough to cast shadows that highlighted surface hazards, yet bright enough to provide excellent visibility for the descending spacecraft. This constant sunlight was essential for thermal management. The spacecraft and the explorers' suits were designed to reflect the intense solar radiation, preventing overheating during the 2-week-long lunar day. They never had to endure the brutal, freezing temperatures of the 14-day lunar night, as the missions were strictly short-duration affairs. The primary objective of these early missions was to demonstrate technological supremacy and secure a safe return. The longest stay on the lunar surface was just over 3 days. It was an extraordinary feat of engineering, but it was essentially a brief scientific excursion. The explorers brought everything they needed with them from Earth: They relied entirely on life support systems, batteries, and consumables packed into their spacecraft. There was no attempt to utilize local resources, simply because the technology did not exist and the short duration of the missions made it unnecessary. It was a closed-loop system with a very strictly defined expiration date upon arrival. Despite these limitations, the scientific return was staggering. The hundreds of kilograms of rock and soil samples brought back to Earth completely revolutionized our understanding of planetary formation. They revealed that the Moon and Earth share a common, violent origin, formed from a massive collision billions of years ago in the early solar system. However, the samples also confirmed a sobering reality about the equatorial regions. They are bone dry. The sun-baked plains contain almost no volatile compounds, and certainly no accessible water. For a long-term base, this lack of resources is a monumental barrier. Transporting water from Earth costs tens of thousands of dollars per single liter. A sustainable presence requires a paradigm shift. We cannot operate a permanent outpost if it relies on a continuous, incredibly expensive supply chain from our home planet. We must learn to live off the land, a concept known as in situ resource utilization. And to do that, we must leave the familiar equatorial plains behind forever. The legacy of those early missions provides a foundation of knowledge regarding orbital mechanics, spacecraft design, and basic lunar surface operation. But the hardware designed for the sunlit equator is fundamentally unsuited for the dark, freezing, and rugged extremes of the lunar poles. A complete redesign of exploration architecture is required. This brings us to the ultimate destination of the Artemis program, a region that has fascinated astronomers for decades, hidden in shadows and shrouded in mystery. It is a place that holds the key to humanity's future in the solar system, but it will fiercely resist our attempts to conquer it. Welcome to the lunar South Pole. The geography of the lunar South Pole is unlike anywhere else on the moon. Because the moon's axis of rotation is only slightly tilted relative to the sun, the solar angle at the poles is extreme. The sun never rises high in the sky. Instead, it perpetually hovers just at or below the horizon, casting incredibly long, shifting shadows. This unique geometry creates a landscape of absolute contrasts. Elevated regions, such as the rims of massive craters or towering mountain peaks, can be bathed in near-constant sunlight for months at a time. These areas, sometimes called peaks of eternal light, offer a vital resource for future explorers. Reliable, continuous solar power. Establishing a base on one of these sunlit peaks would provide the enormous amounts of electricity needed to run habitats, scientific instruments, and life support systems. Solar arrays could track the sun as it slowly circles the horizon, ensuring a steady flow of energy. But the true prize of the South Pole lies just a short distance away. Lying deep within the craters that pockmark the polar landscape are the permanently shadowed regions, or PSRs. Because of the low angle of the sun and the sheer depth of these craters, sunlight has not touched their floors for billions of years. They are ancient, undisturbed abysses, completely isolated from the warmth of the solar system. These permanently shadowed regions act as massive thermal traps. Over the eons, comets and water-rich asteroids have bombarded the lunar surface. While any water deposited near the equator would instantly boil away into space, water molecules that migrate into these dark polar craters are instantly frozen solid, trapped forever in the deep freeze. Orbital probes, such as the Lunar Reconnaissance Orbiter, have used radar and neutron detectors to peer into the pitch blackness of these craters. The data they returned was groundbreaking. Beneath the thin layer of surface dust lies a treasure trove of volatile compounds, including millions of tons of pure, ancient water ice. This water ice is the absolute holy grail of modern space exploration. It is the single most important resource for establishing a sustainable, long-term human presence beyond Earth orbit. With access to this ice, the entire paradigm of space travel shifts from exploration to settlement. The South Pole is no longer just a destination, it is an oasis. However, the very conditions that preserve this precious resource also make it incredibly difficult to extract. The permanently shadowed regions are some of the most hostile environments ever targeted by human engineering. To harvest the ice, we must send machines and humans into environments that defy our conventional technological capability. The juxtaposition of the sunlit power peaks and the frozen, resource-rich craters creates a highly complex operational zone. A future lunar base will likely be split across these two extremes. Power generation and communication arrays will sit on the high ridges, while mining operations plunge into the freezing depths below. Connecting these two zones requires traversing steep, unstable slopes in near total darkness. It is an immense logistical nightmare. Every piece of equipment, from the smallest rover joint to the largest habitat module, must be engineered to withstand the brutal realities of the lunar South Pole. Let us examine the first of these great hurdles, the extreme cold. The darkness inside the permanently shadowed regions is absolute. Without an atmosphere to scatter light, there is no ambient glow, no twilight. Stepping into the shadow of a crater rim is like stepping into a void. This lack of solar radiation results in temperatures that are almost incomprehensible to the human mind. At the bottom of these polar craters, temperatures can plummet to minus 230 degrees Celsius. To put that in perspective, it is significantly colder than the surface of Pluto. It is one of the coldest known locations in the entire solar system, hovering just a few dozen degrees above absolute zero. At these extreme cryogenic temperatures, the fundamental properties of materials begin to change. Standard aerospace metals, which perform perfectly well in Earth orbit, become exceedingly brittle. A minor impact or sudden stress that would normally cause a slight dent can instead cause the metal to shatter like delicate glass. The cold also wreaks havoc on moving parts. Traditional liquid lubricants freeze solid instantly, essentially welding gears and joints together. To operate robotic mining equipment in the PSRs, engineers must develop dry lubricants and innovative mechanical designs that function smoothly without freezing or seizing up in the cryogenic vacuum. Electronics are equally vulnerable. Standard microchips and batteries lose their efficiency and eventually fail completely when exposed to such severe cold. Keeping the internal systems of a rover or a spacesuit warm requires an immense amount of energy, creating a frustrating paradox when operating in regions cut off from solar power. To survive the lunar night or extended missions into the shadowed craters, equipment must rely on alternative heat sources. Radioisotope heater units, which use the natural decay of radioactive materials to generate steady warmth, are essential. These compact nuclear heaters keep vital components from freezing solid during the long, dark periods. Furthermore, the extreme temperature differentials pose a massive threat. A rover traversing from a sunlit peak at over 100 degrees Celsius down into a shadowed crater at minus 200 degrees experiences a devastating thermal shock. Materials expand and contract rapidly, stressing structural joints to their absolute breaking point. Designing spacesuits for these conditions is an engineering nightmare. The new Artemis generation suits must provide incredible thermal insulation without becoming too bulky or rigid to move. They must incorporate highly advanced active heating and cooling systems to maintain a stable internal environment for the explorer, regardless of the external extremes. Every single piece of hardware destined for the lunar South Pole must undergo rigorous testing in cryogenic vacuum chambers on Earth. These chambers simulate the brutal environment of the PSRs, pushing materials and electronics to their limits. Only the most robust and innovative designs will survive the uncompromising cold of the lunar frontier. Surviving the cold is only half the battle. Once a vehicle or an explorer manages to maintain its thermal equilibrium in the darkness, it must then navigate an environment that is physically treacherous. The geography of the South Pole is a jagged, chaotic mess, presenting a severe challenge to mobility and safe landing operations. Unlike the relatively smooth, flat plains chosen for the early lunar landings, the South Pole is heavily cratered and extraordinarily rugged. Billions of years of asteroid impacts have churned the surface into a chaotic jumble of towering mountain ranges, steep-walled craters, and massive boulders the size of multi-story buildings. Finding a safe, level area large enough to touch down a massive landing module is incredibly difficult. The landing systems must be vastly more intelligent and autonomous than their historical predecessors. During the final seconds of descent, optical cameras and LiDAR scanners must rapidly map the terrain in high definition. These hazard detection and avoidance systems are critical. If the spacecraft detects a boulder or a steep slope directly beneath it, it must autonomously divert its trajectory in a matter of milliseconds. There is no time for mission control on Earth to intervene. The communication delay makes real-time human piloting utterly impossible. Once safely on the surface, moving around presents another enormous challenge. The steep inclines of the crater walls are covered in loose, unconsolidated soil. Rovers risk losing traction, sinking into the soft dust, or even flipping over if they attempt to traverse a slope that is too steep. Mobility architectures must be entirely re-engineered. Visual navigation is severely hampered by the extreme lighting conditions. The long, harsh shadows cast by the low sun angle create bizarre optical illusions. A shallow depression can look like a bottomless abyss, while a dangerous ridge might blend seamlessly into the background. Relying solely on optical cameras is a recipe for disaster. Furthermore, there is no GPS system orbiting the moon. Terrestrial rovers rely heavily on satellite positioning, but lunar vehicles must navigate using alternative methods. They use star trackers to determine their orientation and advanced computer vision algorithms to recognize local landmarks and track their movement across the rugged surface. In the permanently shadowed regions, even visual landmark recognition fails. Rovers venturing into the darkness must carry their own powerful light sources. But the intense backscatter from the highly reflective lunar dust can blind optical sensors. Navigation in the abyss relies heavily on active radar and inertial measurement units. The physical exertion required for humans to walk in this terrain is immense. Even in 1/6 gravity, climbing steep crater walls in a heavy, pressurized spacesuit is exhausting work. The metabolic load on the explorers must be carefully monitored to prevent overheating and severe fatigue during long-duration extravehicular activities. To mitigate these risks, uncrewed robotic scouts will map the most treacherous areas before humans ever set foot there. These highly autonomous drones will identify safe paths, locate high-concentration ice deposits, and lay the groundwork for human arrival. They are the essential vanguard in our conquest of the South Pole. But as explorers and machines traverse this jagged landscape, they agitate a microscopic enemy that is perhaps the most pervasive and insidious threat on the entire moon. It is a hazard that coats every surface, infiltrates every seam, and threatens both mechanical integrity and human health. We must now talk about lunar regolith. Lunar dust, scientifically known as regolith, is entirely unlike any dust found on Earth. Terrestrial dust is constantly subjected to weathering. Wind and water erode the particles over time, rounding their edges and making them relatively smooth. The moon, however, has no atmosphere, no wind, and no flowing liquid water. Instead, lunar dust is created by micrometeorite impacts over billions of years. These tiny hypervelocity impacts smash the lunar rock into microscopic fragments, melting them briefly before they cool into jagged, glass-like shards. The resulting regolith is incredibly abrasive, essentially acting like a fine grit sandpaper. Adding to the danger, the constant bombardment of solar radiation leaves the regolith highly electrostatically charged. This static charge causes the microscopic glass shards to cling aggressively to almost any surface they come into contact with. It coats solar panels, obscures camera lenses, and works its way into mechanical joints. During the early lunar missions, the destructive power of this dust became immediately apparent. Within just a few days, the abrasive regolith began to wear away the protective outer layers of the spacesuits. It jammed zippers, compromised airtight seals, and severely degraded the performance of essential life support equipment. For a long-term Artemis base, where equipment must function reliably for years rather than days, dust mitigation is a critical engineering priority. If left unchecked, the regolith will destroy habitats and vehicles from the outside in. Engineers are developing active dust repulsion systems to protect sensitive hardware. One promising technology involves electrodynamic dust shields. By running high-voltage alternating currents through incredibly thin wires embedded in surfaces, engineers can create a traveling electric field that literally sweeps the charged dust particles away. This technology could keep solar panels clear and optical sensors functional. But the threat is not just mechanical, it is a severe biological hazard. If explorers track this dust into the pressurized habitat, it becomes airborne in the microgravity environment. Inhaling these microscopic, razor-sharp particles could cause severe respiratory issues, similar to silicosis or black lung disease on Earth. To protect the crew's health, habitat architectures must feature advanced airlock designs. One concept is the suit port, where the spacesuit remains entirely outside the habitat, attached directly to the wall. The explorer climbs into the suit through a hatch in the back, ensuring the dust-covered exterior never enters the living space. Strict decontamination protocols will be a daily reality for the Artemis crews. Advanced filtration systems, magnetic scrubbers, and rigorous cleaning procedures will be required to maintain air quality. Conquering the lunar dust is absolutely essential for the long-term sustainability of any human outpost on the moon. While the dust attacks from the surface, another hidden danger threatens the structural integrity of the base from below. The lunar landscape may appear frozen in time, geologically dead, but it is actually remarkably active beneath the crust. The next major challenge for the Artemis generation is dealing with the tremors of the moon. During the Apollo missions, astronauts deployed a network of seismometers across the lunar surface. For years, these instruments transmitted data back to Earth, revealing a surprising truth. The moon is seismically active. It experiences moonquakes, and some of them are surprisingly powerful and remarkably long-lasting. There are several types of moonquakes, including deep tremors caused by the gravitational pull of the Earth. However, the most concerning for a lunar base are the shallow moonquakes. These occur relatively close to the surface and are caused by the gradual shrinking of the moon as its deep interior slowly continues to cool. As the moon shrinks, its brittle crust fractures, creating thrust faults, where one section of rock is pushed up over another. The lunar South Pole region has a significant concentration of these active faults. When these faults slip, they generate shallow moonquakes that can register up to a magnitude 5 on the Richter scale. While a magnitude 5 earthquake on Earth is moderate, a moonquake of the same magnitude is far more destructive. Earth has liquid water and heavily fractured rock that quickly dampens seismic energy. The moon, being dry and rigid, rings like a bell when struck. The vibrations from a shallow moonquake can last for several hours. Subjecting a pressurized habitat to continuous intense shaking for hours is a massive engineering concern. Continuous vibration can weaken structural joints, compromise airtight seals, and disrupt sensitive scientific equipment. The foundations of any permanent structure must be designed with advanced seismic isolation technologies. Furthermore, the rugged terrain of the South Pole exacerbates the seismic danger. The steep walls of the polar craters are highly susceptible to landslides triggered by moonquakes. A sudden avalanche of regolith and massive boulders cascading down a crater wall could instantly annihilate mining equipment or robotic outposts below. Before laying the first foundation for the Artemis base, geologists must conduct extensive seismic surveys of the South Pole. They need to identify active fault lines and unstable slopes to ensure the chosen location is safe. Choosing the wrong site could lead to catastrophic structural failure during a prolonged seismic event. Architects are exploring flexible, modular designs that can absorb and dissipate seismic energy. Inflatable habitats, constructed from highly durable, multi-layered advanced textiles, offer a significant advantage. Unlike rigid metal cylinders, an inflatable structure can flex and sway with the tremors without cracking or losing pressure. Ensuring the physical stability of the base is paramount for the safety of the crew. But even if the habitat stands strong against the tremors, the dust, and the cold, the mission could still fail if the explorers are cut off from Earth. The unique geometry of the South Pole creates a severe challenge for maintaining communication. During the Apollo era, communication was relatively straightforward. Because the missions were located near the equator on the near side of the moon, the Earth was always visible high in the lunar sky. This provided a constant, direct line of sight for radio signals, ensuring unbroken communication with mission control in Houston. At the lunar South Pole, the situation is drastically different. From this vantage point, the Earth sits very low on the horizon. Depending on the specific location and the moon's slight orbital wobble, the Earth can frequently dip below the horizon entirely or be obscured by towering mountain peaks and crater rims. When the Earth drops out of sight, direct radio communication is instantly severed. Operating complex machinery, conducting dangerous extravehicular activities, or managing a medical emergency without the support and oversight of mission control is an unacceptable risk. Continuous connectivity is absolutely vital for mission safety. To solve this problem, the Artemis architecture relies on a robust orbital infrastructure. A network of relay satellites positioned in highly elliptical lunar orbits will be deployed. These satellites will act as communication bridges, receiving signals from the South Pole base and beaming them back to the deep space network on Earth. The cornerstone of this orbital network is the Lunar Gateway. This small space station will orbit the moon, serving as a staging point for lunar descents and a vital communications hub. It will ensure that the explorers on the surface always have a reliable link to support systems, regardless of the Earth's position on the horizon. However, even with relay satellites, the sheer bandwidth required for a permanent base is immense. High-definition video feeds, massive streams of scientific data, and complex telemetry from autonomous robots require next-generation communication technologies. Optical communication, using highly focused lasers, is being tested. Laser communication offers exponentially higher data transfer rates compared to traditional radio waves. It allows for vast amounts of information to be transmitted almost instantaneously. But pointing a narrow laser beam across hundreds of thousands of kilometers requires incredible precision and perfectly clear lines of sight. Despite these advancements, the inherent time delay remains. It takes roughly 1.3 seconds for a signal to travel from the Earth to the Moon, and another 1.3 seconds to return. This nearly 3-second round trip makes real-time remote control of fast-moving vehicles or delicate robotic operations extremely challenging and often impractical. Consequently, surface operations at the Artemis base must be highly autonomous. Rovers and mining equipment must have the artificial intelligence to navigate terrain, identify hazards, and execute complex tasks without constant human intervention. The explorers themselves must be trained to handle unexpected crises independently. This shift towards autonomy marks a profound psychological change for the crew. They are no longer just executing commands from Earth. They are independent operators on a hostile frontier. The mental resilience required to live and work in such extreme isolation is just as critical as the physical hardware that keeps them alive. We have explored the daunting obstacles, the Brugi, the treacherous terrain, the destructive dust, the seismic tremors, and the communication hurdles. It is a formidable list of challenges that will cost billions of dollars and immense effort to overcome. So, we must ask the fundamental question, why are we doing this? The immense effort and risk required to conquer the lunar South Pole are justified by one singular overriding objective: the acquisition of water ice. This ancient, frozen resource hidden in the shadowed craters is the transformative element that makes permanent deep space habitation a realistic possibility rather than a science fiction dream. Water is incredibly heavy. Launching just a few liters of water from Earth's deep gravity requires massive amounts of rocket fuel and costs an exorbitant amount of money. Sustaining a crew of astronauts for months or years would require a continuous, financially crippling supply chain of water tanker rockets from Earth. By mining the millions of tons of ice trapped in the polar craters, the Artemis base can sever this expensive dependency. The raw ice can be extracted, melted, and extensively purified to provide a constant supply of safe, clean drinking water for the crew. It is the first critical step in situ resource utilization. But drinking water is only the beginning. Water is the chemical foundation for life support. Through a process called electrolysis, the purified water can be split using electricity generated by the sunlit solar arrays. This process separates the water molecules into their constituent elements, hydrogen and oxygen gases. The oxygen gas is, of course, vital for breathing. By producing oxygen on site, the habitat can maintain its life-sustaining atmosphere indefinitely without needing heavy oxygen tanks shipped from Earth. The base becomes a self-sustaining oasis in the vacuum of space, capable of supporting a growing population of researchers. However, the most revolutionary application of this extracted water lies in propulsion. When liquid hydrogen and liquid oxygen are combined and ignited, they create an incredibly powerful chemical reaction. They are, in fact, the exact same highly efficient propellants used by the main engines of massive launch vehicles. This means the lunar South Pole can function as humanity's first extraterrestrial refueling station. Spacecraft arriving from Earth can land, refill their empty tanks with locally produced lunar propellant, and then launch again. Because the moon has only 1/6 of Earth's gravity, launching from its surface requires far less energy. This fundamentally alters the economics and logistics of deep space exploration. Spacecraft no longer need to carry all the fuel required for a round trip from Earth. They can fly to the moon, refuel, and then embark on much longer, more ambitious missions into the outer solar system. The moon becomes a gateway, not just a destination. Beyond water, the regolith itself can be utilized. Scientists are developing techniques to extract metals like iron, aluminium, and titanium directly from the lunar soil. This raw material can be fed into advanced 3D printers to construct habitat shielding, spare parts, and infrastructure right there on the surface. In situ resource utilization transforms the hostile lunar environment from a deadly adversary into a provider of essential life-giving elements. It is the ultimate key to breaking the tether to Earth. By mastering the extraction and refinement of these resources, we take the most critical step towards becoming a multi-planetary species. The Artemis program, with its focus on the South Pole, is a monumental undertaking in its own right. However, it is essential to understand that the moon is not the final objective. Hey! Everything we are designing, building, and testing in this brutal environment serves a much larger, even more ambitious purpose. The lunar South Pole is humanity's ultimate proving ground. It is a harsh, unforgiving laboratory where we will perfect the technologies required to survive in deep space. The life support systems, the autonomous rovers, the dust mitigation strategies, and the resource extraction methods must all be validated here first. Our true long-term destination is the red planet, Mars. A journey to Mars will take several months, and the explorers will be entirely cut off from Earth's immediate assistance. If a critical life support system fails on Mars, there is no quick rescue mission. The technology must be flawlessly reliable. If we cannot establish a sustainable, safe habitat a mere 3 days journey away on the moon, we have absolutely no hope of surviving a multi-year expedition to Mars. The moon offers a relatively accessible environment to learn how to live off-world, allowing us to make mistakes and solve problems closer to home. The challenges of the lunar South Pole, the eternal darkness, the extreme cold, the abrasive dust, and the psychological isolation will forge a new breed of explorers and engineers. The solutions we invent to conquer the moon will directly translate into the hardware and operational procedures that will eventually take us to Mars. We are witnessing a profound historical transition. The era of the brief scientific sortie, characterized by the magnificent Apollo landings, is giving way to the era of permanent human settlement. We are shifting our perspective from simply visiting other celestial bodies to actually inhabiting them. The legacy of Apollo taught us how to leave our home planet and reach another world. It was a triumph of human ingenuity and courage. Now, the Artemis generation faces an even greater challenge. Artemis must teach us how to stay, how to adapt, and how to build a sustainable future among the stars. The journey ahead is fraught with immense danger. The lunar South Pole will test our technology and our resolve to the absolute breaking point. There will be setbacks, failures, and moments of profound doubt. But the rewards for pushing through these immense difficulties are limitless for the future of humanity. By conquering the darkness, the cold, and the dust, we secure our place in the cosmos. We transform from a single-planet species vulnerable to extinction into a spacefaring civilization with limitless potential. The resources of the solar system await us, and the key to unlocking them lies buried in the shadows of the lunar poles. The next great leap for mankind is not a single step, but a permanent foothold. I am Dr. Sachi Vale, and this has been a special presentation by Science Aura. Thank you for joining us on this incredible journey to the lunar frontier. Keep looking up, and never stop exploring the wonders of our universe.